Okay, so we'll start. There's no warm-up problem today. We're just going to jump right into doing some definitions, and today we're going to finally learn how to do derivatives the quote easy way. So the hard way of computing a derivative to a function at a point A is to say, take the average rate of change about smaller and smaller intervals near that point, and then try to sort of guess what we think those average rates of change are approaching as the interval becomes smaller and smaller. So today we're going to learn our derivative rules, which are going to help us compute derivatives of things like polynomials or exponential functions, just by using these kind of tricks. And so if this were the other calculus course, I would probably give some kind of motivation and proofs behind how these rules were developed. What we're going to do is just learn the rules and how to use the rules. Okay? So the first one, let me think, do I have any announcements? Okay, yeah. The first one, so derivative of a constant. Okay, so say we have y equals f of x equals c. When I write c, it's a placeholder for some number. I want to remind you guys that there's a big difference between this c, which is a constant, and this x and y, which are variables, okay? X and y are inputs and outputs. The c is just some number.
Is that y?
I'm sorry?
Is that y? Like, y equals x?
Yes, this says y equals f of x equals c. So c is just some number. It could be like 3, 4, 5, -1, something like that. But it stays constant no matter what. X and y can change all over the place, but c has to stay constant. So the derivative of a constant function, we would write it as maybe dy dx, or f prime of x, or sometimes we write it like this. We'll write d dx of f of x. Sometimes we'll write it like that, where we consider the derivative as kind of being like a function. Okay, and these things are all going to be equal to 0. Okay? So that's the easiest derivative that you can possibly do. The derivative of a number is just 0. Okay, so for example, we could take a look down here at problem number 1a. We're supposed to differentiate. That means take the derivative of f of x equals 175. I would say f prime of x is equal to 0. So that's just a constant. Okay, so constants just go away. They become 0. The derivative of a linear function is slightly more complicated. So say we had y equals f of x equals, say, mx plus b. Then the derivative, which we might write dy dx, or more likely we'll write f prime of x, we would say that that is equal to m. Okay, so the derivative of a linear function is just the slope of that function. The derivative of a linear function is the slope of that function. So for example, we could try b and c now. B is a line with slope 19. Not b. Well, yeah, problem 1b has f of x is equal to a line with slope 19. So f prime of x is just going to be 19. Okay, I haven't gotten to the b part yet, but let me talk about derivative of a sum or a difference first. Okay, so if we have two functions, f of x and g of x, are functions, then d dx of, in parentheses, f of x plus g of x is equal to f prime of x plus g prime of x. Okay, so if we have two functions being added together and we take the derivative of their sum, it's just the sum of the derivatives. Okay, and this is not trivial. There's some substance in this definition here. Okay, it's somewhat surprising that this derivative function is going to act in this kind of linear way. It's sort of surprising. Okay, but this is why when we do the derivative of a linear function mx plus b, this is why the b goes away. We do the derivative of mx plus the derivative of b. And the first rule I said was that the derivative of a number is just 0, which is why when we do part C here, we can split this up. We can do the derivative of the 2 and then do the derivative of 6t. Okay? So my f prime of t here is just going to be the slope of this line. 2 plus 6t is just a line with vertical intercept at y equals 2 and a slope of 6. The derivative is just going to be the slope. It's equal to 6. Alright, I think we can fly through the rest of these problem 1 problems. So we got f of x equals negative 2. What's the derivative of negative 2 going to be? Yeah, just 0. So, I might write dy dx equals 0. Alright, how about negative 27t? We're talking about problem 1e here. How do I get the derivative of negative 27t? Yes, we would write it dy dx maybe, and what would go on the other side of the equal sign? 0. Not 0 in this case. What's different between part D and part E? What's the difference between those two? Yes, Yasmin? Yeah, so, yeah, I suppose we could think of D and E as both being kind of linear functions, right? D is a linear function, it's just a horizontal function, which is why if we were to take the derivative of that line, the slope of it would be 0, which is why when we have just a constant, it goes away. But there is a bit of a difference between D and E, and it's the presence of this t here, okay? The presence of this t. This means that part E is a linear function with a non-trivial slope. By non-trivial, I mean it's not 0. So it has some kind of slope. So the derivative in this case is going to be just the slope. It'll be negative 27. I really hope that weed whacker stops soon. Okay. Last one. Looks like the trickiest of the bunch. We've got g of x equals 25x plus pi. Well, being that I just learned that the derivative of a sum or a difference is just the sum of the derivatives, what am I going to get when I do the derivative of just 25x? Yeah, 25, right? So I might write this g prime of x equals 25 plus, now I want to talk about the derivative of pi. What do we think?
0.
Yeah, 0. Why is it 0? Yeah, because pi is just a number. So we do the derivative of a number and get 0. That's kind of been like a common theme in our class so far. Pi is just a number. Okay. Yeah, this lesson might not take as long as I thought. Are there any questions on the rules we've learned so far? We did rules with a constant, rules with a linear function, sum and difference. Oh, I forgot the last one. Constant times a function. If we do d dx of c, some number, times the function f of x, we get c times the derivative of f of x. Okay? So if we take a function, multiply it by some number, the derivative also gets multiplied by that same number. So if we know f, and we know the derivative of f, the way we find the derivative of c times f is just by taking the derivative of f and multiplying by c. Okay? So it's basically like you can just pull it out, like a GCF. Okay, we'll have an example of that later on, I think. Yeah. Okay, so questions about these first 4 rules? Okay. Well, then we'll move on to the power rule. This is everyone's favorite rule. And I'm going to write it in sort of general notation. So if we want to do the derivative of, that's what this d dx means. What I've written down so far just means do the derivative of what is inside the parentheses. And what I'm going to put inside the parentheses is x to the power n, where n is just a number. So n is some number. It's a real number. Meaning it could be negative, it could be fractional, it could be transcendental like pi, it could be something really crazy. Right? So n is just some number, well, with the exception of 0. Let me be really careful here. We'll say some real number not equal to 0. Yeah. Then the derivative of x to the n is just n times x to the power n minus 1. Okay? So we take the old power, we multiply it down front as a constant, and then we decrease the power by 1. Okay, we just decrease the power by 1. So, using this new rule here, who can help me apply that rule to problem 2a? We've got x to the power 8 and we want to do the derivative of it. So what should I put on the right-hand side here using this rule? Mia? Sorry? 8. Anything else? Yeah, 8x to the 7th. Exactly. We just took the old power, we multiplied it down front, and we decreased our power by 1. Okay, this is pretty much the simplest application of the power rule that we could have. Okay. When I have a fraction type of situation like in part B, what I'm going to want to do is be a little bit careful. Okay, because I haven't defined yet what it means to take the derivative of a fraction of functions, right? What I see here is the fraction of the function f of x equals 1 being divided by the function g of x equals x cubed, or something like that. And I haven't really talked about what it means to do the derivative of a fraction yet. The only thing that I have said is that if we have x to some power, I can do the derivative of x to some power. So, before I started on this thing, I need to write this as x to some power. What should my power be? Exactly, -3. I have to write it this way because my rule says the derivative of x to the power n will follow this form. What I have here, highlighted in blue, is not a function which looks like x to the power n unless I write it in this way. And having this -3 power is gonna present us with a difference in our derivative, okay? So let's see what we're gonna have. I'm just gonna take that number and multiply it down front. So f prime of x equals -3 times x, and what should the new power be? -4, decreased by 1. Okay, and if you really wanted, you could rewrite this as -3 over x to the power 4 again. Okay, so what I'm trying to point out with this example is that if we want to apply the rule, we have to be in the setup that allows the rule to be applied. So sometimes we got to rearrange our problem a little bit to make it rule friendly, is what's really happening here. So I made it rule friendly by writing it in a way that looks just like how it looks in the rule, and then I applied the rule in the way that it should be applied to functions of that form. Okay, so let me really quickly describe for you guys a common mistake that I see students make on a problem like this. I'll add a page so that we don't have to get real cramped here. Add a page. Okay. The common mistake that I see students make is they say, okay, f of x equals 1 over x cubed. So f prime of x, we just do the power rule, so we get 1 over 3x squared. Done. Can someone tell me what's wrong with this method? Sorry?
Still a fraction.
Yeah, it's in a fraction. I applied the rule in a kind of unfair way. The rule said as long as your function looks like this, the derivative will look like this. Well, I started with something which didn't look like what the premise of the rule requires us to do. So don't make this mistake. I see it nearly constantly. We gotta treat fractions with a little bit of care. Alright, next up I've got the square root of x. Well, I don't know how to do the derivative of a square root of a function. I know how to do the derivative of a function which is x to some power. Any ideas on what we could do? Yeah, Emma?
Well, the square root just means it's x to the 1/2.
Yeah, exactly. Square root of x is the same as writing x to the 1/2. So just like before, I just took this thing and I rewrote it in a way that's friendly for using this rule. So now I just multiply down by the power, so f prime of x will be equal to 1/2 times x. And now I'm going to do 1/2 minus 1. Okay, so 1/2 minus 1 equals 1/2 x to the -1/2. So if I was to write it properly, I'd write maybe 1 over 2 square root x. Alright, so step 1, rewrite in a rule-friendly fashion, then apply the rules. Alright, finally we get to use, for part D, we're finally going to get to use this rule about the derivative of a constant times a function. Okay, what we have in this problem is 2 times x to the power 4.5, which is to say we're multiplying this constant 2 times the function x to the 4.5. We know how to do the derivative of the function x to the 4.5, and we know that the derivative of a constant times that function will just be the same as doing the constant times the derivative. So combining this green rule here with the power rule on this problem, we know that d dx of f of x will be equal to d dx of 2. I guess I should have started this a little bit higher up. I'm going to run out of space. I'm moving that there. Would be d dx of 2 times x to the 4.5. Now here's where I'm applying my constant rule. This is equal to 2 times d dx of x to the 4.5. So I got rid of that pesky constant, and now the only job I have left to do is the derivative of x to the power 4.5. This is getting a little repetitive at this point, but we'll keep going on. 2 times 4.5 times x to the 4.5 minus 1 is 3.5. So this is all to say this is equal to 9x to the 3.5. Okay, so constants are not really an issue. We can just let them float along. Okay? So my only real job for this problem was to just do the derivative of x to the 4.5 and then multiply it by 2. Okay. Let me stop for a second and ask for some thumbs. How do we feel about this ddx notation? Is that confusing? Let's have thumbs up for not so confused, thumbs down for like pretty confused. Okay, I'm seeing some confusion going on, so maybe I'll talk about it a little bit. Okay. So, what this ddx thing is called, well, the fancy mathematical word we have for it is linear operator. It's an operator in the sense that it's like it's kind of like our conveyor belt, where it's like a box, okay? What goes into the operator, and the reason we call it an operator and not a function, is a function takes numbers as an input and it outputs numbers. Okay, so we would have something like 3 going in and then 6 coming out, and then that function we would call it 2x. Okay, that's what's going on with a function. The difference here for an operator is that an operator is taking functions as input. Okay, so we take an entire function into the operator, and the operator does something to it, and then out pops f prime of x. Okay, so when I write d dx of f of x, this is kind of similar to when I write, say, maybe f of 2 equals 6, maybe. So here's my input 2 into my f function. My output here is 6. For the derivative operator, my input is a function, and the output is the derivative of that function. Yes, Ashlyn?
What's the distinction between d over dx from dy over dx?
Great question. I can sum it up as follows. If we have y equals f of x, then d dx of f of x is equal to dy dx. And here's why. If we take y equals f of x, remember, if we have an equal sign, if we do the same thing on both sides, we can keep the equal sign, right? For example, if we multiplied both sides by 2, that's fair game, and the equal sign would still be valid. If we took the natural log of both sides, the equal sign would still be valid. And if we apply the derivative operator on both sides, then we would also still have the equal sign. And to answer your question, Ashlyn, dy dx is just the shorthand notation for this left-hand side. Okay? So, the derivative operator takes a function as input, and it outputs another function, which is the derivative of that function. You'll get more used to this notation as we go along, I think. If you have any more questions about it, though, please let me know. All right, for now we'll move on to part E. Well, we've got f of x equals x squared over 4 plus 3. We want to do the derivative of this function. So I'm going to use 3 rules. Okay? The first rule that I'm going to use, I've got a plus here. I'm just going to do the derivative of the left part first and then the derivative of the right part, okay? If I have a sum of 2 functions, I can just add their derivatives, and that's going to be the derivative of the sum. Okay, so, well, I guess I'll use 4 rules. The next rule I'm going to use pertains to the derivative of the number 3. We know that the derivative of a constant will be 0, so I know that the derivative of this 3 here is just going to be 0. And lastly, I'm going to use 2 rules to do the derivative of the left summand, x squared over 4. One rule that I'm going to use is the constant rule. I can think of this as 1/4 times the function x squared. So the constant, which is being multiplied, will float along, and I will just take that constant and multiply by the derivative of x squared. So let's do it. I can rewrite this as 1/4 x squared plus 3. And if I want to do the derivative, I would say, okay, f prime of x equals, well, I know the 1/4 is just going to hang out. Now I need to write the derivative of x squared. That's 2x. And now I need to write the derivative of 3. That's 0. So I get 1/4 times 2x. It's just x over 2. All right, as you get faster and faster with the power rule, you'll start to kind of get the hang of this and move a little bit more quickly than this. Typically, if I was going to do this derivative, I wouldn't go through the trouble of rewriting the function as 1/4 times x squared. That's just so you guys can help to visualize it. Later on in the class, I might look at x squared over 4 and say, aha, we apply the power rule and we get x over 2. But that's just something that comes with a little bit of practice, okay? You'll have to use the power rule almost constantly for the rest of the semester. So you will get used to it. Okay, next up. Again, I got to use the constant multiplier rule. I've got this -3 floating out front. So I say, okay, you can't trick me. I'm just going to let that float. F prime of x equals -3. And now I just need to write the derivative of x to the -4th power. What should the derivative of x to the -4th be? Ashlyn?
It would be -4x to -5.
Exactly. -4x to the -5. Okay, so we just applied the power rule. We took the power, we multiplied it down front as a constant, and then we decreased the power by 1. Since it was already negative, it became more negative. So we get 12x to the negative 5th power, or you could write it as 12 over x to the 5th. All right, great. G looks like a doozy, so let's stop for a second and ask for questions. Yes?
Do you have to, like, can you leave it as 12x to the negative 5th, or do you need to rewrite it?
Good question. I think usually my policy on things like exams or quizzes or whatever, of course we're not having quizzes this semester, usually my grading policy is if your answer is equivalent to the answer that I was looking for, I'll give you full points usually. So if I were to ask this question on an exam, I would give full points for the answer 12x to the negative 5th, and I would give full points for the answer 12 over x to the 5th. I would even probably give full points if you wrote down negative 3 times negative 4x to the negative 5th, even though that's not great mathematical practice. Yes, Abhi.
What about on the homework? Because I know it has
Yeah.
to be in a specific form, so if you interfere with one thing off, it like marks it wrong.
Yes, that's what I was about to discuss. Unlike me, the Wiley Plus homework is not so forgiving, and I'm aware of some issues with the way that Wiley Plus grades problems in this chapter in terms of having things in the right form. I'm going to do my very best to avoid them on the homework, but it's possible that something's going to slip onto there, so I need you guys to be vigilant. If you see something that's just like not quite so right, try to bring it to my attention, and you know, if you're just getting it wrong because you're wrong, I'll let you know. But it's possible that there will be some things on the homework that are messed up like that. Hopefully I'm planning on going through the problems myself and making sure, but it's possible that something can slip through. But yes, on an exam, anything that's equivalent to what I might call the true answer, I'll give you points for. Okay, any other questions? All right, we'll move on to G. All right, now we've got a sum of two functions and then minus another function. So let me ask you guys the following. This rule here, which I said about derivative of a sum and difference, if I have f and g are functions and I add them, then the derivative is just, I take the derivatives of those two functions and add them. So let me ask, does anybody, well, let me ask, do we think that this is going to work when we're adding and subtracting three things together? Who thinks yes is going to work? Let's have hands raised. How about not sure? Okay. It is going to work, and I'll explain the kind of thought process. First, we consider f of x as the difference between two functions. This function we'll call g, and we'll subtract from that the function h. So the derivative of a difference of functions would just be the derivative of g minus the derivative of h. And now g is itself the derivative of g is the derivative of a sum of functions, maybe k and j. Okay? So when I do the derivative of g, I would get k prime plus j prime minus h prime. Okay, so the trick is to first think of the first two summands as a function, apply the rule to get the derivative of that function minus the derivative of the thing on the end, and then when we compute the derivative of g, we again split it up using the exact same rule. So it does work if we have 3 or more summands. The only thing we have to do is take the derivative of each thing and then either add or subtract the derivative of the next piece of our summand. Okay, so this would be all equal to k prime plus j prime minus h prime. All right, so now we've determined that we can in fact use our sum and difference rule on sums of more than just 2 summands. So let's actually do this. So I'm going to erase this now. Is everybody okay with that? So I have a little bit more room to write. Okay. Bye-bye. All right, so first up, what I'm going to do is rewrite some of these things in a more rule-friendly fashion. The cube root, I'm going to rewrite as x to some power. What should the power be?
1/3.
Yeah, 1/3. How about 1 over x squared? How can I write that as x to some power? Sorry?
X over 2.
Not x over 2. X to the power negative 2. That's right, Mia. Thank you. So, we rewrite these things in a rule-friendly way. Now all 3 of our summands are, I think, rule-friendly. So let's go through. What's the derivative of x to the 1/3 power going to be? Yasmin? Yeah, 1/3 x to the negative 2/3 plus, how about x to the negative 2? What's that going to become?
Negative 2x to the negative thing.
Yeah, negative 2x to the negative 1/3. And the last thing, about minus 5x. Yeah, minus 5. So if I wanted to write it in a nicer way, I might write 1 over 3x to the negative 2/3. Sorry, that should be a positive 2/3 now. X to the 2/3 plus, no, minus 2 over x cubed minus 5. Okay? So, it turned out, when we traced through, this original plus sign did wind up becoming a minus sign, but that's just because the derivative of this positive function, 1 over x squared, we had an extra negative pop out when we used the power rule. So we got our negative 2 there, multiplied. So if we add a negative number times something, it's the same as subtracting that number times that something. Okay, I'm going to skip h. H is pretty much the same. But we will talk about I. We love using pi in our examples. What do we think about x to the pi? Can I apply one of my rules to this function? Yasmin?
Yeah, you would just use the regular power rule because pi is just a number, so you just have pi times x to the pi minus 1.
That's exactly right. So Yasmin says pi is just a number, and we have a rule about x to some number and how to do the derivative thereof. The rule says I should take that number and multiply it down front. And then I should have x. And then I should decrease the number in the power by 1. How could I write that? As a power. The answer is simpler than you might think. Yeah, Ryan?
Pi minus 1.
Yeah, pi minus 1 is how we're going to write it. We don't have a symbol for pi minus 1, so the best we can do is just write pi minus 1. Okay. Questions about that last problem? Or any of these problems? No? Feel okay? All right, sweet. Well, we have done a ton of derivatives so far. Let's have a problem where we actually have to do a little bit more work. All right, we're supposed to find the equation of the tangent line at x equals 1 to the function f of x equals x cubed plus 2x squared minus 5x plus 7. Okay, so we have a polynomial function here, which consists of sums of non-negative integer powers of x. And we're supposed to find the tangent line at x equals 1. So, the tangent line to f of x at the point x equals a has equation t of x equals, and I'd like to see if there's anyone in the class who can help me fill out the rest of this equation. The equation which represents the tangent line to f of x at x equals a. Ashlyn?
Is it the same thing as the tangent line approximation or is it different?
That's exactly right. It is.
Alright, so wouldn't it be f of a plus f prime of a times x minus a?
That is exactly right. Okay, thank you, Ashlyn. So, f of a, let me rewrite that f. That's a really bad f. F of a plus f prime of a times x minus a. This is the tangent line. It's the same exact equation we use for tangent line approximation because that's exactly what tangent line approximation is. We're using the tangent line to approximate the function. So the equation that we use for tangent line approximation of the function is the same as the equation of the genuine tangent line. So we're supposed to find the equation line at x equals 1. So we should have, in our case, t of x should be equal to f of 1 plus f prime of 1 times x minus 1. So that's how we're going to figure it out. So there's a little bit of work to be done, which I'll do up here, in terms of figuring out what are the component parts of this equation. The things we're going to need to figure out are what is f of 1 and what is f prime of 1. So let's do f of 1 first. Well, we just plug it into the function, right? We got 1 cubed plus 2 times 1 squared minus 5 times 1 plus 7. So we get, what, 1 plus 2, that's 3, minus 5 is negative 2, plus 7 is positive 5. Sure hope I did that right. All right. And now we need to figure out what f prime of 1 is. Okay. So I kind of wish that I could just plug 1 into some function, except I don't have the function yet, so I need to compute it. Okay, that's what I'm going to do. So to find f prime of 1, we need to plug 1 into f prime of x. So we know, well, let me start with f of x. F of x is equal to x cubed plus 2x squared minus 5x plus 7. Let's figure out f prime of x. Okay, I've got a sum of 4 different functions here. I can just do the derivative of each one individually. First up is x cubed. What's my derivative? Yeah, 3x squared. What rule did you use to do that? The power rule. All right, how about the next one? 2x squared. How do I do that derivative? Yeah, Mia?
4x.
Yeah, we're going to get 4x. You used 2 rules there to do that one. Which rules did you use? Can you give me one of them?
The derivative of a constant.
Yes, the derivative of a constant times a function. The constant just floated. And then, do you know what the other rule was?
What's the power rule?
Power rule. Okay, so we combined 2 rules for that one. We did the constant and the power rule. All right, now I get a minus derivative of 5x. That's a linear function. It's just going to be the slope of that linear function. It's going to be minus 5. By the way, that's consistent with the power rule, because if we do 5 times x to the power 1, the 5 floats, and then we get x to the power 0, which x to the power 0 is just 1. Anything to the power 0 is just 1. So we get, so we did a derivative there. So it is consistent with the power rule if you want to just view it in that lens. What's not consistent with the power rule exactly is this plus 7, which becomes a plus 0. Okay, so now we have our function, our derivative, and we need to plug in 1. So f prime of 1. So we're finally answering the green part of our question. Is equal to 3 times 1 squared plus 4 times 1 minus 5. So we get 3 plus 4 is 7 minus 5 is equal to 2. So, plugging in, we found f of 1 was equal to 5, so I'm just going to put a 5, plus f prime of 1 we determined was equal to 2, times x minus 1. Okay, so we found the equation of the tangent line. I highly recommend committing this formula to memory, okay? Knowing how to find the equation of the tangent line is important, okay? Tons of exam problems and homework problems ask for finding the equation or use it to approximate the function at some point, something like that. For example, we could say, for example, that f of 1.1 is approximately t of 1.1, which is equal to 5 plus 2 times 1.1 minus 1, which is equal to 5 plus 2 times 0.1, 0.2 is equal to 5.2. So that's a way that we can use the tangent line to approximate the value of f at a point nearby. We could also just take 1.1 and plug it into f. If we put in 1.1 here, we're going to get a number which is fairly close to 5.2, but not exactly 5.2. All right, that's it for today. If you have questions, then you can hang out for a little while after class, or I have office hours on Friday. Aaron also has a session tomorrow as usual. Yeah, of course. Yeah.
Sorry, one question I have is when we're finding f prime of x, what is 2x to the power of 2 become 4x?
Okay, great. So your question is about this term right here, this 2x squared?
How do you get 4x?
Sure. So let's just treat it as if it was its own function.
Okay.
2x squared, right? Two rules were used to do this part, right? So the first one was that the derivative of a constant times some function is the same as just taking that constant and multiplying it times the derivative of that function. So if I want to do f prime of x, that's the same as doing d dx of 2x squared. Now the crucial rule that was used here is now we can pull the 2 out. Okay, so this part here underlined in this kind of salmon color says, literally, do the derivative of 2x squared. What this right-hand side says is do the derivative of x squared, then multiply by 2. And the rule was that they're equal. So how do you feel about doing the derivative of x squared?
So then it would just, you would bring the 2 out in front and then subtract the, you would subtract 2 minus 1, and then that would just be 1, so, and then you would multiply 2 times 2x, and then it would be 4x. Okay.
Exactly.
Sometimes I just need to see it.
Yeah, no, that's okay. Like I said, some of these things, we're going to go through them rather quickly. So you got to slow me down if there's something that you don't get, because probably there's other people in the class who also don't get it.
Gotcha.
Okay, any other questions?
No, I don't think so.
Oh, weren't we? Hang on one second. Let me stop the recording.